Today we're presenting our work in the dengue AI predicting disease spread. This is Mirvat and my teammate Yusuf. And first we'll start by describing our problem statement. So dengue is a major public health issue in the tropical regions. Given the historical weekly records of dengue cases in two cities, San Juan in Puerto Rico and Iquitos in Peru, along with associated environmental variables such as precipitation, temperature, humidity, and so on, we built a machine learning model that predicts the number of dengue cases for future weeks. So our goal here is that our input is the climate or environmental features with the lags, which we will get into details later, and the output is the number of dengue cases per week. However, we need to note that our main goal here and our target while we were doing this project was not to just score higher in the challenge, but to actually solve the actual problem. So why does this problem matter? Well, if the health authorities can anticipate spikes or outbreaks in dengue early, then they can allocate medical resources. Also, early warning could reduce disease and burden. And if outbreaks are predicted, preventative measures like mosquito control can be deployed more strategically. And also, the model can also help to uncover which environmental variables, lags, or conditions are strongly predictive of the outbreak patterns. So, what's the value of a good machine learning model? Well, better accuracy in predicting case counts means fewer surprises. You reduce false alarms, wasting resources, and missed outbreaks. If the model can predict one or more weeks ahead reliably, it gives actionable lead time. The split, as we mentioned, we have data from two cities, San Juan and Iquitos. So what we did is that we actually split the data by the city. Why did we do this? Is because we expect that the dengue transmission or the disease to behave differently in different locations. But then later, for the competition test set, we merged the predictions from the respective models. For the train validation split, we actually split our data into training and validation using two methods. The first is the time series cross validation, where the model is trained on expanding window of past data and tested on future data splits. And the second is that we left the last 20% out for pre-processing. We dropped the week of the start date column in our first model because it was redundant. We only used the week of the year for the feature engineering. We used the week of the year for the sinusoidal projection, which will help us to detect if there are any seasonal patterns. This will be discussed in detail later. We then checked for the null values. When we checked for the null values, we performed forward fill to eliminate these null values. However, we wanted to note that there were several weeks that had null values continuously, and simple imputation by forward filling might be inaccurate due to the multi-week gaps in the observation. So forward fill would assume the missing values and it would give it the values like the previous ones, which might be inaccurate for many weeks consequently. We then checked the correlation between features and we found that there were very highly correlated features in both data sets. We then solved this using PCA, which will also be discussed in detail later in the presentation. We then we made a baseline model. The baseline model was before we did any feature engineering to compare the results after we did the feature engineering. So the models we used for the baseline was linear regression, ridge regression, and random forest regressor. And we processed only the numeric features. We did like median imputation and scaling. Results before the feature engineering were really bad. As you can see here during the graph, the actual and the predicted values were not close and it couldn't predict the peaks. We then decided to do the feature engineering. So what we did was, first we decided to do the lag features, then we did autoregressive lag features, and then we did the sinusoidal features. So we started with the lag features. So for the lag features, we first created a delayed version of the climate variables 1 to 16 weeks to capture the mosquito life cycle and the incubation effects. Why did we do this? Is that because when the mosquito would bite the patient, the symptoms would appear weeks later. It doesn't have to appear right now. So there was a clear lag in the data. So what we did was we made like a create temporal features function. It builds the lag features from 1 to 16 weeks, and we compute the rolling average and the standard deviation 4 weeks and 12 weeks for short-term and seasonal effects. We then add the lagged dengue cases to capture any outbreak persistence. We then compute the exponential moving average for the recent trends. We applied this to the data for both data sets as case counts lag features are proxy for contagiousness. So if we deploy the model in a real-world scenario, the number of reported cases of the previous week is easily attainable. So we decided to use this information and make an autoregressive model that would actually make use of this. So what we did is we created an autoregressive model that added autoregressive features to capture the time dependence and the outbreak persistence. So To create the interaction features, we selected the top 5 numeric weather variables, and then we multiplied them with the lagged case counts. We then captured the weather times the contagiousness interaction, and we applied this to our 2 datasets, San Juan and Iquitos. So now we have an autoregressive feature. So results after the feature engineering were actually much better. We tried this feature engineered data on random forest, XGBoost, gradient boosting, ridge regression, and lasso regression and neural networks. And surprisingly, lasso regression performed the best. And this is for the other dataset. And we also noticed a similar regressive features actually performed well. We did a feature importance analysis. As you can see here, they were the most important features. We then decided to try the sinusoidal time features. What is a sinusoidal time features? It actually just adds cyclic features to represent the week of the year as a sine or cosine waves. We did this using the week of the year feature from our dataset, and we created sinusoidal transformation to represent the cycles annually, semi-annual, quarterly, and bi-weekly. We did like graphs, sine graphs and cosine graphs for all these 4, so in total we had like 8. And these are the results. So results after the sinusoidal time features, it actually did improve the performance. As you can see here, the mean absolute error decreased in almost every model, and same for the other dataset. We also performed cross-validation. We performed the time series cross-validation with 5 folds. There was no clear winner, and the lasso seems to be the most stable with the lowest variance and average mean absolute error value. We also did an ensemble model. So what we did is that we averaged the prediction from all our previous models, and actually here the weight was equal. However, we do believe that if we try boosting, it can be tuned and can perform better. Could have better performance if we weighed the results from the model. To decorrelate the features, we performed PCA. We actually tried PCA with different ranges of variance from 80% to 99%. And after we found the cumulative explained variance, we decided that 95% was our best option, as it gave us a reasonable number of components with a reasonable variance. This was for 2 datasets. And surprisingly, PCA did not perform well. So when we actually removed when we decorrelated the features, it performed worse than when we had the correlated features in the dataset. So our final results on the competition or the test set was that the model with the autoregressive features had 33.16 mean absolute error, and the one with the non-autoregressive features had a 27.64 mean absolute error. So, and also here to compare what we did. So for the comparison, here's the baseline versus the ensemble with the autoregressive features. So in the beginning, we showed the baseline model with very bad predictions, and the peaks were not aligned at all in the graphs. But then our ensemble model with the autoregressive features actually has a very much smoother. Main takeaways is that the autoregressive model performs much better than the one with the lagged total cases in real world scenarios, and the autoregressive model was able to predict the trends and the outbreaks. It was also able to predict when the outbreaks end. Also, the other model predicting almost constant values all the time, it wasn't able to predict the disease outbreaks. And finally, we want to say that the benchmarks could be misleading sometimes.